Hello, welcome back to the second video in 6.6 integration involving inverse trig functions and advanced integration techniques. And our objective is to go ahead and integrate specifically with advanced techniques for the next three examples. For this example, we're going to reintroduce this idea of completing the square. And the idea of completing the square you did in accelerated math 2 with quadratics when you wanted to put a quadratic in standard form into vertex form. And how we do this is we take our b term and we go ahead and we divide by 2 and we square it. So 4 divided by 2, this is 2. And then we will go ahead and square this. This gives us 4. So in order to complete this square, I need to have a 4. So 1 over x squared plus 4x plus 4. That is a perfect square, and I can go ahead and factor that, and I'll do that in a second. Right, but if I have the plus 4, here I don't have to introduce it. I can just steal it from this 8. So I have another 4 here, right? So this 4 plus 4 is still 8. So I just broke off a 4. If you didn't have something to break off of, you can go ahead and add something in. But again, if you're going to add it, you need to subtract it as well to keep it balanced, okay? So I'm going to go ahead and factor this here. So I'm going to integrate, and I have 1 over, and factoring that, this gives us x plus 2 times x plus 2. So I have x plus 2 squared plus 4. And now, the whole reason that I went ahead and did this is that this is tan inverse form, where our u is x plus 2 and our a value is 2. Okay, so this will give us 1/2 tan inverse of x plus 2 over 2 plus our constant. And we're done. So that is involving completing the square. Kind of a hint of why I would want to do this. Again, if I'm going to do u substitution, making the denominator u, I still have a hook-on factor that's nowhere present in this integrand. So that's kind of why we completed the square here. Here's a practice example. Go ahead and integrate this. Start by completing the square. Okay, hopefully you went ahead and tried this one. Here is the solution. So if you're going to go ahead and complete the square, if we take our linear term, the 6x, if we take this, we divide by 2 and then square it, that gives us 9. So I'm going to go ahead and add in 9, but if I add in 9, I also have to subtract 9. So you'll see the format here, what they did is they went ahead and pulled out the negative. So I have x squared plus 6x plus 9. Now when I add this 9 in here, really this is subtracting 9. So now I have 7 plus 9 here, and that's how they got that. Okay, so that one's a little more complicated than the simple example I did as the example, but that's completing the square nonetheless. Okay, so pause the video if you have, if you weren't able to complete that square, and try to finish out the problem from here. Okay, and the rest of the solution, this is sine inverse or arc sine form, where I have a 1 in my numerator, our a value is 4, and our u value is x plus 3. So here's our solution. Sine inverse of x plus 3 over 4. And since we do have bounds, this is definite, so we have to evaluate at those bounds. And our final answer would be pi over 6. All right, lastly, I have 2 more examples. Example number 10, we've kind of already seen this advanced technique where we split our integral. So I'm going to split this as 3 over the square root of 1 minus x squared dx minus the integral of x over the square root of 1 minus x squared dx. So I'm splitting this because, again, if I'm going to do some substitutions, say u is 1 minus x squared. Well, the derivative of this is negative 2x dx. So that doesn't account for my numerator. So I'm not going to do that. So here I'm just going to split the terms in my numerator. And our first one over here, this is sine inverse form. Okay, so this is going to be equal to 3, and it's exactly sine inverse of x. Okay, minus. Over here, I am going to do u substitution. So here I'm going to say, okay, I'm going to let u be equal to 1 minus x squared, and then du is equal to negative 2x dx. So it looks like I need to introduce a negative 2 and balance with a negative 1/2. Okay. And so let me rewrite this actually. So I have a plus 1/2 integral of 1 minus x squared to the power of negative 1/2 times negative 2x dx. And here is our hook factor that's going to go ahead and go away. So this gives us 1/2 times 1 minus x squared to the power of positive 1/2 divided by 1/2. And again, these two terms are going to cancel, and we get our plus c. So our final answer, that stays the same, is 3 sine inverse of x plus square root of 1 minus x squared plus c. Okay. All right. Last example, example number 11. Example number 11 is the weirdest and kind of most out-of-the-box integration method that you'll probably see. Here I have the integral of 1 over e to the x plus 1 dx. So I just want to kind of go through some integration methods that probably where you'll start. You'll probably start by saying, hey, what if u is equal to e to the x or e to the x plus 1? And I'll show you the problem with using e to the x as a substitution, is that the derivative of this, u prime or du, the derivative of e to the x is e to the x. So you almost have to have another e to the x present in order to be able to integrate or to do some type of substitution. And I definitely don't have an integration rule for this type of integrand. So here's what we're going to go ahead and do. I'm going to add an e to the x into my numerator, and I'm going to balance it with a negative e to the x. So really, I'm adding nothing into my numerator. Now, why would I want to go ahead and do this? Well, I'm going to use the same idea that I did in the last one, is I'm going to go ahead and split it. So I'm going to take these first two. So I have e to the x plus 1 over e to the x plus 1 dx. Okay, minus the integral of e to the x. So this is our second integrand. So e to the x over the denominator, e to the x plus 1 dx. Now, why did I do that? Well, if we look here, our numerator and our denominator are exactly the same. Well, e to the x plus 1 divided by e to the x plus 1 is just 1 dx. And hey, isn't that just x? Yes, it is. I almost wrote dx again. Why? I don't know. Okay, now we still have a second integrand. And look what happened. I was telling you, hey, if you're going to do any substitution with e to the x, right, if I'm going to let u be e to the x plus 1, I have to have the derivative of this, which is e to the x times the derivative of dx. Okay, so I have it. So this format, right, is this is u prime or du over u form, right? Which is just natural log of u plus c. Okay, so this is going to be minus natural log of the absolute value of u, which is e to the x plus 1, plus our constant. And we are done. All right. So that's going to do it for this video on advanced integration techniques. Just kind of summarizing the techniques we went over. We went over completing the square, which is here. Sometimes you can, if you have a quadratic where substitution's not working, if you can complete the square, you can put it in a tan inverse form, and that's what we did here. And then we went ahead and we looked at splitting our integrands, the numerator. If you have two terms in the numerator, you can go ahead and split it if that helps you kind of simplify the integrand. Okay, and that's what we did here. The last case, again, when you have e to the x's, sometimes it helps to add in an e to the x, but remember you have to balance it as well. Okay, that's going to do it for this video. Catch you next time. Peace.